Welcome to the Automatic Tools tutorial. In this tutorial, we describe targets, automatic marking, automatic referencing, automated surface triangulation, point cloud NURBS surfaces, and coded targets. Photomodeler includes automatic tools that are designed to improve the efficiency of certain types of projects. These tools are designed mostly to aid in the creation of high-density digital models, but they are also beneficial in other applications. In this tutorial, we will demonstrate the use of the automatic tools. We start by working with a project named footauto1.pmr. This project can be found in the Tutorial Auto Tools folder. In this project, we are using the automatic tools to create a detailed model of a human foot. The foot is a complex curved surface that would be difficult to model using Photomodeler's regular marking tools. It could be done, but it would require many hours of marking and referencing. The automatic tools can cut this work down to a few minutes. The project has already been partially set up. On the screen, we review a photo and the initial results in the 3D viewer. Reviewing Photo 3, we can see that there are a number of control points that have been marked and referenced, and the photo has been oriented. The foot is covered with a fairly dense grid of circular targets which have not been marked yet. The 3D viewer window shows the solved camera stations and the solved control point data. To use the automatic tools, you must follow certain procedures when setting up the object for photography. This involves the use of circular targets. We maximize Photo 3 and zoom to fit for a closer view of the targets. The object surface must be covered with circular targets when doing photography. These targets can come in the three forms. The first form of targets is stick-on natural light targets, which are small circular dot stickers placed on the object. These can be purchased from any stationery store. The second form of targets is stick-on retroreflective targets. These are circular targets that light up when a camera flash is used. These are useful in complex environments where there are other circular objects in the background that need to be separated out. Retroreflective targets are available from some survey supply companies or can be made out of material available at most sign shops. The third form of targets is projected targets. These are targets on slides that are projected onto the surface using a slide projector. EOS Systems has a number of dot slides available in different grid densities. All forms of targets must have good contrast with the background in order for the automatic target marker to find and mark the points successfully and with accuracy. There must also be 6 to 10 points that are readily identifiable and distinct from any grid of targets which can be manually referenced. These manually referenced points are used to orient the project photos. The automatic referencing tool requires the photos to have reasonably good orientations. If the Coded Targets module is installed, this first manual referencing stage can be skipped. In this project, we have used control points seen here along the rectangular base to orient the project. You can mark and reference regular non-control 3D points across the photos to orient them if you are able to find enough points. In addition to these point requirements, there is the requirement that sufficient good quality photographs be taken. Ideally, you would like every target to appear on at least 3 photographs. The camera positions for these photographs should be in a triangular shape. Please see the help file and manual where the proper photography for automatic target projects is discussed. In this project, we have a total of 7 photos, and each has been oriented using the set of control points. There are 3 automatic tools in Photomodeler: automatic target marking, automatic referencing, and automatic surfacing. The Weld Unreferenced Points function is also available for use in cleaning up some of the auto-marked points. First, we will work with the automatic target marking tool. We close Photo 3 and the 3D viewer and open Photo 1. We adjust the photo window position and zoom out so we have some extra screen space. We right-click over the toolbar and choose the Auto Tools option. The 4 automatic tool icons now appear on the toolbar where we can easily access them. We click the first icon to bring up the automatic target marking dialog box. We adjust its position so we can see the photo window as well. The automatic target marking tool works by searching through an image and finding all circular targets that have good contrast with the background. Once it finds these targets, it automatically marks them. Here in the photo, we have used stick-on natural light targets. As you can see in this project, the curved surface of the foot would require a lot of manual marking and referencing work if you were to use Photomodeler's regular tools. The region section defines what area of the photo will be searched for targets. By default, the region is the full photo area. We can choose a specific region by clicking the Pick Region button. The dialog box disappears and the cursor changes to the Pick Region cursor. We click and drag in areas surrounding the foot. The dialog box reappears, and we can see that the region coordinates are updated defined by the region we selected. The automatic marking tool will only search for targets in this section of Photo 1. In target identification, we can set up how the program will identify the targets. This process is called segmentation. In most cases, the default automatic option is chosen, and you can move on to the next step. Here, we will quickly demonstrate the manual option. The manual option would be used if the automatic option had trouble finding the targets on our photos. We select the manual option, and notice that the image now appears as black and white. In the manual settings section, it tells us that the targets should look white on the photo. So we have to tell Photomodeler that we are using dark targets. Then the black and white settings reverse, and the targets now appear as white. We then use the threshold slide bar to adjust visibility so that all the targets are visible and there is minimal noise in the image. In this project though, the targets are well defined and we can use the automatic option. In the target marking section, we have to set the maximum diameter size of the target in pixels. To set this size, we can press this button, and the instructions dialog box appears, telling us to zoom in on the largest target we can see. We click OK, then drag and select a region around this target, and it automatically fills in the size value of 45 in the dialog box. We increase this to 50 because the other photos in the project will likely have targets that are larger than 38 pixels, and we are going to use the same settings for every photo to speed up the process. The minimum diameter size is set as a percentage of the maximum size. The minimum size then is 25% of 50 or 12.5 pixels. The circle shape number tells Photomodeler how circular the target should be in order for them to be marked. A setting 1.0 represents a perfect circle. A value of 0 would be a line, and values between are ellipses. If we look at some of the targets on the photo, the perspective of the photo causes some of the circular targets to appear as ellipses. So we set the threshold at 0.5, allowing the marker to use these targets. Note that if you do not set the correct value, it is easy to rerun the marking with new settings until all the points are marked. In almost all cases, the subpixel target marking option should be used. This is the high accuracy marking feature that finds the best target center given the image data. There are two options for subpixel marking, the centroid method and LSM, which stands for least squares matching. LSM is a bit slower, but it is far more accurate, so this is the option used more frequently. The coded target section here will be discussed later in this tutorial. Now that we have set our parameters, we click the Mark Points button. It automatically searches the set region for targets and marks them in subpixel mode. We close the dialog and zoom in for a closer look. We can see the points are marked in the center of the targets. Some of the targets were not marked. For some of these targets, their shape was not circular enough to meet the parameters we set. For other targets, there was not enough contrast with the background for them to be picked up. We open Photo 2 and activate the automatic marking dialog. This time, we will leave the region setting as the full photo and leave all the other settings. We click Mark Points. We open Photo 3 and repeat the steps. We do the same for the remaining photos. When finished, we close the dialog box. All our photos have now been marked using the automatic marking tools. With all the photographs auto-marked, we can begin the automatic referencing process. Reviewing the photos, you can imagine the amount of manual work it would take to reference all of these points across the 7 photos. We click the automatic referencing icon from the toolbar and the dialog box appears. There are 5 sections in this box where we can enter our settings that tell automatic referencing how to work. Note that automatic referencing works on oriented photographs only. This project has been oriented through the use of the base points and control data. In the first section of the dialog, we tell the program which points we want to reference. We choose all points in the project. Points that have already been referenced, such as the control points, will not be referenced again. The All Points in Layer option is used when you have placed your points from all photographs into layers. This allows you to distinguish different parts of an object or scene and reference them separately. This can be useful when you are modeling some 3D objects that have points on more than one side. The foot is a 2.5D shape, meaning that it is relatively planar but also has some elevation. In this case, we don't need to place the points in layers. In the Parameters section, the search distance is used to control how the program decides which points match with which point across the photographs. This distance number is the default based on the current reference points in the project, which are the 6 control points. The Perform Search Distance Double Iterations box provides an option to double the search distance setting number. Referencing will go through the photos searching at the first setting, and then it will try again at double the search distance number. This should result in referencing of a few additional points that were not referenced the first time through. In the Minimum Number of Photos section, we tell the program that a point must appear on a minimum of 3 photographs in order for it to be referenced. The number can be changed to a higher number to increase the robustness of the automatic referencing. We can have the points automatically named once they are referenced. This will help us find those points later for troubleshooting and editing purposes. We can also set them to Do Not Process, and they will not affect the accuracy of the project during global optimization. We will leave all options in these 3 sections at their default settings. These settings are designed to reference the maximum number of points. This may occasionally result in a few referencing mistakes. If we are to increase the setting for minimum number of photos and turn off the doubling distance setting, this would result in less overall points referenced, but fewer mistakes as well. In most cases, the correct set of parameters will result in perfect referencing of all points. In the Referencing section, we are provided with some information about the project. It tells us we have 7 oriented photos, with 611 marks across those photos. There are 0 points on 2 or 3 photographs. This will change once we do the referencing. There are 6 points on 4 or more photographs. This refers to our 6 control points. We click on the Execute Referencing button, and the referencing process begins. After it finishes working, it updates the information in the referencing section. There are now 0 points on only 1 or 2 photographs. There are 6 points that appear on only 3 photographs, and 106 points that appear on 4 or more photos, many of these on all 7 of our photos. This column tells us the changes that occurred from its previous state before referencing was executed. We close the dialog and open a 3D viewer to view the results. We turn on points and lines, and in the Settings tab, we change the point size to 2 and click OK. We maximize the 3D viewer and use the controls to study the general shape of the foot. The overall shape seems fine. We zoom in for a closer look. As we rotate, we can see a point that appears to be sticking out more than it should. This point looks to have been misreferenced. If we select it, we can see on the status bar that it appears on 3 photos only. If we had changed the minimum number of photos to 4, this point would not have been referenced. We can check the photographs where this point appears to see where the mistake is. With the point selected, we right-click and choose Open Photos Showing Selected. Photos 1, 4, and 5 are opened, and the point is highlighted in red. We study the point in the 3 photos, and it is obvious that the point in photo 1 does not match the point in the other 2 photos. We could try and fix the reference, but the easiest solution here is to just delete the point. There are enough marked and referenced points on the foot, so this does not have to be fixed. We reopen the 3D viewer window and maximize. In the 3D viewer options, we turn off the layer called Control Base. We had previously set up this layer to include the 6 control points only. We now get a 3D view of the marks on the foot only. The model looks good so far and is ready for detail to be added to it. Next, we will use the Automatic Surfacing Triangulation tool. With the 3D viewer open, we select Edit, Select All Marks Objects in Active View. With all the points selected, we click the automatic surfacing icon from the toolbar. The automatic triangulation dialog appears. This feature will produce triangular surface elements between the points. It creates what is called a TIN, or Triangulated Irregular Network. In the Which Points area, we have two options. We do not want the control points to be surfaced, so we choose only selected objects. In the Methods section, since the foot is a 2.5D shape, we choose 2.5D object points. We click OK. In the 3D viewer options, we turn on Surfaces and click OK. We review the model in the 3D viewer. We can see that the surfaces have been created on the model. Overall, the surfaces appear to have calculated well. As we take a closer look, we notice this one surface back here does not look quite right. Occasionally, you'll find with the automatic triangulator that you'll get an incorrect triangle from your perspective. We will just select that triangle and delete it. We study the surfaces for any other problems. We review our resulting triangular irregular network of points. We click on the surfaces to show that these are individual triangular surface elements. This surface project can be exported in its current state to any program that accepts these triangular elements. Another powerful feature that works well with dense point grids on a complex surface is the point cloud surface. First, we will delete all the triangular surfaces. We open a surface table. All the surfaces are listed here. We select all of them by pressing Ctrl and A on our keyboard, and then delete them by pressing the Delete key. We close the surface table and review in the 3D viewer. We are back to the state where we have just the points. We select all the points by pressing Ctrl A, then select Surface, Create Point Cloud from the toolbar. It applies a best fit, low-order NURB surface through the points. We review and can see that the fit is not perfect. We are able to make adjustments so the fit is better. We select the surface and click Properties of Selected. We move the dialog box off to the side so we can view the model. In the Point Cloud section, we look at the Max U and Max V spans. By increasing the number of spans, you can control how much the shape is allowed to change within its extent. In this case, the V direction is across the width of the foot, and the U direction is along the length. We increase the spans to 11 and 5, and click Apply. The model updates, and the surface now seems to fit quite well. We close the dialog box. We review the model in the 3D viewer, and look at the number of points above the surface and below the surface. From that, you can determine whether you have made sufficient number of spans to fit the surface you want. This is a single NURB surface, not a triangulated one. It can be exported to the various formats that can handle NURBS elements. NURB surfaces can also be exported in triangulated form for those formats that do not handle NURBS natively. This concludes the foot project using the automatic tools. We've shown you how to use tools for automatic target marking, automatic referencing, automatic triangulation surfacing, and NURBS surfacing. In this segment, we will work with coded targets. Coded targets are an add-on module to Photomodeler Pro 5.0 that can be purchased from EOS Systems or your regional dealer. Coded targets are a type of circular target which also have a code ring around it with unique bits that uniquely identifies it. If you have the Coded Targets add-on module, the targets can be generated and printed using the Generate Coded Targets dialog under the File menu. This dialog is used to generate a PostScript file containing the coded targets of the desired size and type. The PostScript file is then sent to a PostScript printer or into Adobe Acrobat. See the user manual or help file for further details. Here we start with a project called CodedStart.pmr, which can be found in the Coded Target Project folder. This project has already been set up in the Project Wizard. It has the correct camera and 4 photographs. There are no marks and no processing has been done. We zoom to fit the photo and open the automatic marking dialog. We move down to the Coded Targets section. We can have photographs with targets that have no codes, some codes, or all coded. We will use the all coded option in this case. There are different coded sets. We are using coded set 3, which has 12 bits on it. The default parameters are already set up for the coded target size and the circle shape. We press the Mark Points button and it marks the coded target points. We zoom in on the points and notice that each of the points has a number ID attached. This is the coded target unique ID. These IDs are unique to that code that had been read directly from the photographic data. Next, we will see why this is important. We will repeat these steps for the other 3 photos. We open each of them while leaving the automatic target marking dialog open with the same parameters chosen and clicking Mark Points. After it finishes, we close the dialog box and click Window Tile and Zoom to Fit All to view all the windows. If we look at the point IDs, we can see that they have already been referenced. The benefit to doing a coded target project is that PhotoModeler recognizes the coded targets as they are marked and automatically references them, and we can go straight into processing. This greatly speeds up the project setup. To view the result, we open up a 3D viewer with points and camera stations turned on. We can see that we have a 3D result, with solved camera stations and 3D point positions, done without having to do any referencing, manual or automatic. This example demonstrates the strength of coded target projects, quick project setup, and greater automation. Next, we will look at the completed project that started with these coded targets. We open CodedEndPipes.pmr with photos 1 and 2 open and tiled. The photos contain the coded targets, and we have also marked some pipes using the cylinder tool. We open a 3D viewer to view the results. We turn on cylinders with the shaded option and click OK. We use the 3D viewer to review the resulting cylinders. Using the coded targets, we were able to set up a project efficiently and accurately, allowing us to quickly move into modeling of the rest of the project. This completes the Automatic Tools tutorial. We have worked through the topics of targets, automatic marking, automatic referencing, automatic surfacing triangulation, point cloud NURB surfaces, and coded targets.